Each year, Microsoft Research hosts hundreds of influential speakers from around the world, including leading scientists, renowned experts in technology, book authors, and leading academics, and makes videos of these lectures freely available.
Hello, welcome everybody. So it's my great pleasure to introduce Mikolas Janota. So he's going to present some very advanced techniques for solving quantified Boolean formulae. So, and please welcome to his postdoc interview talk.
Okay, so hello everybody. So today I'll be talking about quantified Boolean formulas. And before I do that, let me go back a little bit in time. So there's this famous quote by Leibniz that many of you probably know, where he said, "Let us calculate." And there was this brilliant idea that if we encounter some problem in philosophy or ethics or whatever, we start calculating in some well-established calculus, and we resolve this problem. So, of course, an amazing idea, because it would mean that we could use calculations not only to reason about taxes and groceries, but we could actually really answer some things about the real world. Of course, as some horrible things happen in the meantime. So it was shown that logics are incomplete, and Turing machines are undecidable, and then we have complexity theory that shows that even some very small problems are really hard to compute. Now, the good news is, I think, is that people kept going, so they still kept working on these problems, even though we know they are hard. And the result of this, that now we have machines, or we have tools that really can reason automatically or semi-automatically about some real practical problems. And what I think has been really fruitful is to look at certain fragments of logic and build tools for these fragments, and like this get some really nice results. And today I'll be talking about one such fragment, which is QBF, Quantified Boolean Formula. And of course, I need to say something about SAT before I say something about QBF. So SAT is this little innocuous problem that we have a propositional formula, and we're supposed to find an assignment that makes it true. So you can have something like this x or y and x or not y, and you can set x to true and y to anything, and that makes it true. So this is a really nice and simple problem. Now, QBF is almost the same. You can just write some additional quantifiers. So we can say something like this: for all x, there exists y, that x is equal to y. Now, because we're still in the Boolean domain, we can rewrite any QBF into a propositional format.
So implicitly, x and y are just Booleans.
They're implicitly Booleans. Everything is Boolean, finite, decidable. So the universal quantifier is actually a conjunction, and the existential quantifier is actually a disjunction. It's really, you can imagine this as a shorthand. So if we take this example, and I start inside out, and I start rewriting the inner quantifier, I plug in 0, I mean false, and 1 into the formula, and build a disjunction. And I the same for the conjunction, and I get something that doesn't contain any variables, and I conclude that the original formula was actually true by just purely Boolean simplifications here. Of course, everybody can already see the problem with this. I cannot do this in general because the formula blows up exponentially, right? So this is obviously not the way how to calculate if a QBF is true or not. Now, there's a really nice correspondence between SAT, QBF, and complexity theory for those who like complexity theory. So SAT is NP-complete, and as well QBF with only one quantifier is at the first level of polynomial hierarchy. And as you start writing more and more quantifiers, you're going up in the polynomial hierarchy until QBF in general is PSPACE-complete. Okay? So in QBF, we're moving from NP-complete problem to a PSPACE-complete problem. Okay, so this is a kind of a theoretical classification Now there's also a very nice relation between QBF and two-player games, and this is maybe a little bit less known. For this, we consider QBFs in so-called PreNext form, which just means that we have always a bunch of quantifiers at the beginning and just the propositional part. So it will always look like this. For all, some variables exist, some variables, potentially some more quantifiers, and then only the propositional part. Okay, so this is what we call PreNext form, and I'll stick to this for the rest of the talk. Now, if we want to formulate this as a game, we say that there's a game between two players. One is the universal player, and the other is the existential player. Okay? And the universal player tries to make the matrix, the propositional part, false, and the existential player tries to make the matrix true. And a formula is false if and only if there is a winning strategy for the universal player, and formula is true if there is a winning strategy for the existential player. Okay?
Matrix?
The matrix is just the propositional part.
Why is it a matrix?
Oh, it's just called that way. It's just a name. I mean,
We could call it a formula, couldn't we?
well, I mean, the whole thing is the formula, and
Okay.
I mean,
there's no tabular aspect.
yeah, I mean, yes. So, I mean, you have the formula and the quantifiers. It's called a prenex, and sorry, prefix. Sorry, I'm also got prefix, and the inner part is called the matrix. It's just the terminology that's been used in the community.
And the quantifier is always at the front.
Yes. So this, I mean, of course, in general, you don't need to consider these cases, but for this talk, we just consider.
Are all the universal ones in front?
No.
Oh, no.
It can be anywhere, and the prefix can be as long as you want. Okay. Okay. If we go back to the example we've seen, again, we have only just these two quantifiers. So we know this formula is true. So there must be a winning strategy for the existential player. And here it's really simple. The winning strategy is play the same thing as the universal player did. Okay? So the existential player will wait if U is true or false, and plays the same thing, and that makes the matrix true.
So the order of terms is sort of outside in.
Yes,
Okay.
yes. So actually, if you do not like formulas, you can think about QBF as a two-player game. Okay. Now, so we have these relations. Of course, we should really ask, why are we interested in these formulas, in solving these formulas? So again, let's go back to SAT. So there's this huge success story, which is, I think, quite amazing, that has happened with SAT in the last 2 decades. So many of you, I'm sure, know that in the mid-90s, SAT solvers became really powerful, and they've been used for hardware model checking, reasoning about circuits, more recently bioinformatics, many other things. And I think even more interestingly, they gave rise to new tools for more powerful logic. So SMT really derives from SAT. There's MaxSAT solvers, AnswerSAT programming. And today I will also show you that you can build a QBF solver using a SAT solver as a kind of a black box machine. Now, okay, so we have this huge success of SAT. Now the question is, can we replicate at least a part or some portion of this success with QBF, right? So one thing to observe is that we're really solving a fundamental problem, which I think is positive, right? So SAT is NP-complete. Now we're solving a problem that is PSPACE-complete. And also there's this relation to two-player games. So this is, I think, a good sign that we're really solving a problem that is somehow fundamental. And so any PSPACE-complete problem can be expressed as QBF, right? Of course, there are direct applications of QBF to parts of model checking, circuit synthesis, other things like non-monotonic reasoning and conformal planning. Sorry. And of course, now we, similarly as in SAT, we would like to ask, can we build other tools on top of QBF, right? So can we integrate QBF into S&T solvers, for instance, for quantified bit vectors? Can we do optimizations with QBF? And actually, we already did that partially. And of course, who knows? So I think really the interesting part for me is to build solvers for problems that we don't know yet, right? So this is kind of the motivation. We want to look at QBF and solve QBF formulas. Okay, so let me get a little bit more technical here. So we have seen this parallelism between games and QBF. Now I will introduce this very simple term that will help me later on, which I call the winning move. And this is really very intuitive. I will define it recursively. So if you have just one quantifier, what is the winning move? Okay, so if we are the existential player, the winning move is something that makes the matrix true.
So yeah, this is just a single variable.
Sorry. Whenever I write capital letter, I mean multiple variables.
Right. Okay, so this is a bunch of existential.
It's a bunch of existential blocks.
Okay, that's important. You couldn't phase this with a single variable at a time?
You could, but it's actually nicer to you're not, yeah. Yeah, it's a little technical. I mean, you could, but because actually, if we are the existential quantifier, this is really just a SAT problem, right? We're asking, is there an assignment, right? So there is a direct mapping between one quantifier and a SAT problem.
And phi is a QBF. So the question is, an assignment that makes phi true.
Propositional. No.
Yeah. So in this particular case.
This is just the last quantifier.
So yes. So this is a kind of a recursive definition. So for the base case, it's one quantifier. Okay. So the winning move here is an assignment that makes the matrix true if we are the existential player, and conversely, it's an assignment that makes the matrix false if we are the universal player. So, okay, so this is the contradicting objective of the two players, right? So this is very clear for the one. For the general case, I make it very simple. I say that it's such an assignment that when I plug this in, there is no winning move for the opponent. Okay, so imagine you're playing chess, right? So a winning move is such a move that the opponent cannot find a move to win the rest of the game.
Doesn't that mean that phi is not propositional because the opponent has to have a move after?
Yeah. So this is for that's the rest of the QBF.
Capital phi.
Yeah, capital phi. Yeah, there's a bunch of conventions that are a little tacit here. Okay. Of course, in the opposite case, if I play some move, and the opponent is still able to win the rest of the game, he had played a counter move, right? So this is another term that I'll be using now, right? So a counter move is something that the player was able to play and win the rest of the game, right? So this means that my move was not a winning move because there is a counter move. Is everything okay? Okay, so this is really nice because we don't really need to worry about QBF. This still works with the analogy of two-player games. Okay, and actually, if we have this definition, we can immediately build a very simple QBF solver.
So this definition of counter move doesn't make it only makes sense if you say a counter move for the assignment tau.
Yeah. Yes.
Okay, so to say something is a counter move doesn't make sense.
Yeah, exactly.
Okay.
Yes.
Fine. Yeah.
Very good point. Yes. Thank you. Okay, so now we actually can build a very simple QBF solver using a SAT solver based on these definitions, right? Because for the base case, well, we know how to compute a winning move. Well, if we're the existential player, just run a SAT solver, right? And the SAT solvers are very efficient, so this is excellent, right? If we're the universal player, well, it's also not too much more difficult. We just negate the formula. right? We just want to make it false, so we find a satisfying assignment to the negation. So this is really simple. Now, the problem is, what do we do in the general case? Well, let's just start with this naive algorithm that will just try all possible moves. Okay? So we start with the pool of all possible candidates for moves. There are exponentially many of them, right? Because if we have many variables, there's exponentially many assignments. And we always pick one assignment, we plug it into the formula, and we run recursively this algorithm to test whether there is a winning move for the opponent. If there is a winning move for the opponent, well, we have to keep on going. If there is no winning move for the opponent, we can stop because we have a winning move. Okay, so I mean, this is a kind of a stupid way to play chess. So you play a move, you lose, you go back, and you play another move, and you lose, and you go back. And so this is essentially a backtracking process. I just formulated in this fashion because we will try to refine this approach.
I don't see the sort of the Q-bar duality showing up here somehow. I was expecting to see something getting inverted in the successive.
So what happens here? You plug in the candidate,
yeah,
and that will remove the first quantifier.
Yeah.
So now you have the opposing quantifier at the beginning.
Q isn't used in this algorithm.
Um,
Itself is not used. Is it? Line 10.
It's used in line 8. You're checking for null, which is a negative of having found something.
So actually what happens is it's used at the very end, right?
Oh.
Yeah, because and in the base case. So this is we are assuming that we have these definitions, right, in the for this procedure, so essentially you plug in a bunch of assignments and you test whether it's satisfiable or not at the end, right? Right. So I mean, yes, this is again. So when you plug in the value for the first quantifier, you remove it, and then you move on to the opponent. Okay. Okay. So this is we all agree this is a horrible algorithm. We don't want to use that. Now we can make an observation here that this naive algorithm is not making use of the counter move, right? So we played, and the opponent beat us with something we don't know. I mean, we don't do anything with that, right? We just try different moves, and we're not learning from this experience. So here's an idea how we can learn from this mistake or from this counter move. We will build another smaller QBF, which I call the abstraction. And each time we are hit by a new counter move, we strengthen this abstraction so that we are not beaten by the same counter move again. Okay? So and this strengthening we will call refinement. So here is a pictorial representation what is going to be happening. We have initially abstraction is all possible moves. And each time we are beaten, so we try some candidate move, we're beaten, we strengthen the abstraction and so on until we somehow approximate very well the set of actual winning moves for the actual game, for the initial game, right? And hopefully our next the candidate will be from this set of winning moves. Okay.
Moves for a single quantifier, are they?
For a single quantifier. So it's
somehow but there's lots of quantifiers. So
yeah, so it's a recursion. So this will be done in every level of the recursion. Yeah. So I mean, you can think about this algorithm in different ways. I like recursion, but but of course you cannot. But eventually the levels will go into. There will be as many levels as there are quantifiers, yeah, of the recursion. Okay. Now, how do we do refinement in QBF? So this is a little technical. So imagine you have x's, bunch of variables, for all, a bunch of variables, and the rest of the QBF. Okay. And now we played tau, so we played our candidate move, and the opponent played mu, which is the counter move, right? So if we plug these two in, we're losing. So what we want...
What did that mean? I mean, we plugged the two in, and then somehow we discovered that exhaustively...
Yeah, somehow we discovered.
Somehow we discovered that the thing was false.
Yes, okay. Exactly, yeah. So, I mean, it's the recursion that discovers that. What we will do is, for the next candidates, we will make sure that the candidate move will be a winning move for the following game. We plug in the counter move. Okay, so we consider a simplified game where the opponent is kind of stupid. He plays always the same move. And we make sure we win this game. Okay? So this means that next time he cannot beat us with the same move because we made sure that we are sort of proof that we are robust with respect to this particular move. Of course, we need to somehow be robust with respect to multiple counter moves. So we will be iterating this process. We find a bunch of counter moves. So this is, again, a little bit of algebra or Boolean logic. If we have multiple counter moves, we're the existential quantifier. We plug in these into the games. We have a bunch of smaller games, and we compute a conjunction of these games. So actually, if you look at this from the definition of QBF, what is happening is that here the universe quantifier is being expanded. But what is interesting is that it's not being expanded exponentially, but only as many times as we have iterated our process. Okay? So this is much smaller than the actual expansion that we would have built according to the definition. So this is obviously a weaker constraint, right?
You can only use this at one level of recursion.
Yeah.
So you have to forget all this work when you move to the next level.
Yes, I mean there you can. This is little technical. I mean there's ways how to keep this some information, but then it grows in memory and yeah. But yeah, essentially, let's say we forget. Yes. Okay. Now, okay, just a technical note. When we are the universal player, instead of conjunction, there is a disjunction, which again goes with the. According to the definition, we're essentially expanding the existential quantifier here. This is really just a duality thing. It's not that interesting. Okay.
Is it really dual? I would think that when you're playing as a universal quantifier, then the existential quantifier might make a choice that's sort of a function of what you're doing.
It's really it's completely dual. This is nice about this game perspective, because the existential tries to make it true, and the universal might try to make it false, right? And let's say I relabel false to true, and I relabel true to false. I mean, it's just a label. I mean, it actually doesn't matter that we call it true or false. I'm not sure if that answered it, but I mean, you can have a strategy for either of the players.
Make sure the next candidate is a winning move for blah. Right. Is there a danger that you might have eliminated too many candidates?
No, this is always sound.
If you said, make sure the next candidate is not a losing move for blah, then I'd be with you. But
yeah.
It might be somewhere in the middle, mightn't it?
No. It's essentially what you're saying, if I understand correctly. What we're trying to do is that we're not beaten. This is my terminology that I like to use. That we're not beaten by the same counter move that we have seen so far. So right. So we know the opponent can beat us with foo, and so we make sure the next time we try a new candidate that we're not beaten by foo. This really simple idea.
Foo is now a constant. It's not.
It is a constant. It's a constant.
You can't use max sat to actually generalize the.
Well, you could try to generalize. At this point, I this is, of course, very interesting, but at this point, I don't know of a nice way of doing it. I have some ideas, but it's not that easy. I mean, yes. So, yeah.
Little phi is a proposition here, right? So it's just.
No, this is a QBF.
Little phi is a.
Oh, little phi is a proposition, but this capital phi is a QBF.
Then when you do the conjunction, you're no longer PreNext.
Yes, that's true. Okay, I was hoping nobody spots that.
Quantified prefixes.
Yeah, I mean, so again, there are some technicalities hidden. I have to do the pre-nexting afterwards.
That's going to duplicate all the quantifiers.
Yeah, I'm really happy that you asked these questions. So actually, that's something that what we managed to do. So I mean, this is not shown in the talk, but we managed to do that. We duplicate only the next quantifier. Okay, I mean, maybe we can take this offline, but it's a bit of a technicality. I wanted to, but this is a very good point. We need to pre-next to get rid of this problem, and there is a way how to not duplicate everything, and it is actually, I think, important. But very good point. So okay, so let me get. So if we combine everything together, we get this simple algorithm for solving QBF. So in the base case, it's all the same. We just run a SAT solver to solve the problem. That we've seen is easy, and we know that SAT solvers are fast, so that's amazing. Now, we build the abstraction at the beginning of the iteration, so it's either a conjunction or a disjunction of these smaller games. Now we solve here is the hidden thing that you pre-next. So you solve the abstraction. And now, if we cannot win the abstraction, we're done, right? If we cannot even win the smaller game, well, we cannot win the big one, right? So we stop. However, if we won the abstraction, we need to test that this candidate is really a good candidate, right? So we move on and test if it's a good candidate by another recursive call. So there's two recursive calls here. And if if the opponent is able to find a counter move, we stop. If the opponent is able to find a counter move, we add it to the set of counter moves we are considering. If the opponent is not able to find a counter move, we know that we have a winning move. Okay. Let me stop. Okay, so this is this really nice algorithm. There is a modification that everything is not duplicated in the pre-nexting. I will not show that. I have implemented this in a solver called Rarex. Actually, last year there was a QBF competition, so the solver won the application track, and it's a cactus plot here. So actually, the solver really there's a big difference between the current solvers and what my solver can do.
What are the axes here?
So this is the number of instances, and this is the number, this is a time, this is in milliseconds. So if there is a point here, it means that there were 500 instances solved in 400 seconds. Right, so there were 100 instances solved very quickly, 200 instances still very quickly, and eventually to solve more and more instances, the time is increasing.
So initially there's 1,000 instances, and these are, you can imagine ordering them by how long they took to take.
Yeah, exactly.
To solve. Okay.
Yeah.
So more to the right is better.
Yes,
okay.
Exactly.
And then green is you.
Yes, exactly.
So this is saying you are better.
Yes.
Excellent.
Yes.
Okay.
Yeah. There's always somebody who, essentially, that's the conclusion. Yes. This is, so and the timeout here is 900 seconds. Okay. So I should point out this is an application track. The solver also worked well in other tracks, but I was not the first in those tracks. But I also, because this was part of the FOC Olympic Games, I got a Kurt Gödel medal for this. Okay, so this is a sort of like empirical evidence for this solver being good or definitely interesting to look at, right? And now I'd like to show a little bit of evidence that it's also interesting from the theoretical point of view. So now we have a bunch of techniques for solving QBF, and mainly we can divide them into expansion-based and DPLL-based. So expansion is basically what I showed you now. You take the quantifiers and you expand them according to their definition. DPLL is that you take a SAT solver and you make it work for QBF. Okay, so we have these two worlds, DPLL, expansion. Now the question is, are they different really, right? And there is this popular approach how to decide whether some solving method is different or better than another one, is to look at some corresponding proof systems. So instead of looking at the solvers directly, we define some proof systems that correspond to these solvers. We compare proof systems, and then we can conclude something about the solvers. What do I mean by a proof system? Essentially, you can think of it as a certificate, right? So when the solver stops, it not only gives us yes or no, the formula is true or false, but it also gives us some proof that it is true, it is false, that we can check in polynomial time with respect to the size of the proof. So
Isn't that just an assignment of the quantifiers?
No.
Oh, it would be for existentials, but not for universals.
No.
Oh, yeah. Okay, so you should go on.
Now, of course, I should mention proofs are also interesting as certificates, right, for the correctness. So we don't have to trust the solver. We can just check the certificate. So there's a practical component here, but also we're interested in proof systems for comparing solvers, right? Now, how would a proof system look for expansion? Well, I will omit many details, and I'll just consider this very simple type of formula where we have exist, bunch of variables, one single universal variable, exist, and bunch of variables, and a propositional part. Okay, so let's just look, for the time being, let's just look at this formula, or this set of, or class of formulas. How do we prove it's false? So let's prove it's false. Well, we took our definition of universal quantifier, and we expanded into a conjunction. Now there is this technical issue that has been rightly posed before, that now the third variables are duplicated here. It's no longer PreNext. Well, we can get rid of it. We rename them and push them forward. This operation is called PreNexting. And this is quite standard. So now actually we have a SAT problem, right? We're saying, is there a set of is there an assignment to these variables that makes this propositional formula true? It has more variables, but it's still propositional. Okay, and we know how to refute propositional formulas. We have normal resolution, right? Propositional resolution. Okay, so let's say this is our proof, and it is a proof in the sense that we can check this in polynomial time. You check that the expansion was done correctly, and you check that the propositional proof was correct. And all these steps I can check in polynomial time. Okay. We have a more proper proof system defined in our papers if you're interested, but yeah, let's just think about a proof system for this type of formula that look like this. So we have a proof that shows that the formula is false. Okay. Now, so this is for expansion. Now, what about DPLL? Well, we're in luck here because Hans Kleine-Buning and sorry?
What about DPLL?
DPL. So there is this other family of solvers that are based on the DPLL procedure, essentially on SAT solvers, right? So they extend SAT solvers. And we're asking, is there a proof system that corresponds to this family of solvers? And there is a proof system actually defined in 1995 by Hans Kleine-Buning and colleagues, which is called QResolution. And again, I will not go into the technicalities. It's almost the same as normal resolution. So we have we assume that the matrix is in CNF. Here is a small example. We can resolve as in normal resolution. We can resolve on existential variables. And then there is an additional rule how to get rid of universal variables, that under certain condition we can remove a universal variable, and eventually we get to a bottom, to an empty clause. Okay, so sorry, but I had to skip the formal definition here. It's just for you to have an idea about what is QResolution. Now, we would like to build a formula that is hard for QResolution but easy for expansion. Okay? I'd like to give some ingredients, some idea of this construction here. So what are the ingredients of the proof?
Why would we like to build such a formula?
Because we would like to show that our expansion-based approach is somehow fundamentally different from this DPL approach, right? So I mean, because these proof systems are somehow corresponding to these solvers, right? Mm-hmm. And so if we can show that there are formulas that are hard for one proof system but easy for the other system, it means that it must also be the case necessarily for the solvers, right?
Okay. You mean it's not just an accident in the implementation of the solver?
Yes, exactly. We want to kind of abstract from implementation features, because we know that for any run of the solver, we can produce a proof in this proof system in linear time, right? So whenever we have some information about the proof system, then we can conclude something about the...
Saying if the proof is big, then the solver couldn't possibly cough up the proof quickly.
Yes, exactly. Exactly. Yes, thank you. Okay, so I'll just give some highlights of this construction. So we try to build a formula that's hard for DPLL, meaning QResolution, but it's easy for expansion. Okay, so this really just highlights. Hopefully, it will give you some idea what the proof looks like. So we know that the formula is false. So we want to find some false formula that is hard for the proof system. And we know that for any false formula, there must be a winning strategy for the universal player. Okay? And not only that, we know that from any QResolution proof, it's possible to extract this strategy efficiently from the proof, okay, in polynomial time. And moreover, it is possible to express this strategy as a circuit with bounded depth. Okay? So whenever I have a QResolution proof, I can derive a circuit that represents the strategy for the universal player as a circuit with bounded depth. And we know from circuit complexity that the parity function cannot be expressed as a circuit with bounded depth. Okay? So I mean, the bounded depth circuits, this class is called AC0 in circuit complexity, if you like that kind of stuff. But by AC0, I mean function that can be computed with bounded depth. And now the last important ingredient in this construction is that we can build formulas that force a certain strategy for the universal player. And it's really simple. So we consider this form that we had before, exist x, one single universal variable, some existential variables. And the matrix is constructed from some function f. And we say that it must not be equal to z. Okay? Now there's only single way how the universal player can win this game, and that is by playing f. Yeah? Because whenever x has been assigned a value, the universal player just computes what is f, and that makes this part false, right? So z is equal to f, so this becomes false. Okay, so there we have a formula that is a single strategy for the universal player, and which is playing exactly f. Okay, we put all these ingredients together, and we have a hard problem for QResolution. So we pick f to be the parity function. So we say, okay, we have this formula where the strategy for the universal player is the parity function. We build a QResolution proof, any QResolution proof, and we know that in polynomial time I can construct a strategy that will be a bounded depth circuit representing the parity function. And from circuit complexity we know that this must be exponential. Okay? And of course, this means that everything is exponential. The proof must be also exponential because the strategy is exponential and the strategy is polynomial with respect to the proof. Now, I should also mention that this problem is easy for expansion, and it's, again, it's a little technical, but so you have to trust me a little bit. Essentially, what happens is that you encode this into, let's say, CNF, right? And you expand the universal quantifier, and you just get a formula that says parity must be true, parity must be false at the same time, and then you need to refute it by resolution. That turns out to be quite easy. Okay, so I hope I convinced you that this new algorithm for solving QBF is somehow interesting from both theoretical and practical perspective. So we have some benchmarks where this performs well, and we have some theoretical understanding that this is fundamentally different from the existing solvers.
Which could mean that it's fundamentally better in a few cases that never show up in practice, and fundamentally worse in lots of cases. Doesn't necessarily mean better.
Yes.
Okay.
Yes.
Are you hazarding that it might be better in many common cases?
Well, actually, let me say a few words about this. Okay.
You can postpone the answer to that. It's coming up anyway.
Actually, now I've hidden a lot of details. You can check the papers. So what we did in our last few papers, we defined a bunch of calculi for expansion-based solving. And there are some other calculi for DPL solving. And we built this graph comparing all these different calculi. So now we have these two worlds of calculi that somehow derive from this idea of expansion solving and DPL-based solving. And really, what it boils down to, the information that we can conclude here is that they're incomparable, essentially, right? In the meaning that there is always a class of formulas where one calculus performs fast and the other one fails, but also the other way around, that for the same pairs of calculi, there is another class of formula where it's reversed. Okay, so essentially, what we really want, of course, I think this is a great motivation for people who develop solvers, like myself, I hope, to come up with some solvers that will somehow encompass all these approaches. So I think this been, for me, was tremendously beneficial to do this theoretical analysis, because we can really say that the solvers are not optimal in some sense. Right?
We know no better way than to run the two in parallel and see which comes finishes first.
And actually, it's a little bit worse. There are some calculi here that have no solvers that correspond to it. They somehow generalize these ideas, but they're so even for these calculi, we're still missing solvers. I think. I hope I'm not too far from coming up with some. I have some ideas for this, but it's too early to say anything. Okay, so
Can I just check which side is green on?
So this is the expansion-based solving.
That's
Yes.
what you've been talking about.
Yeah, and then there's the DPL-based solving, the QResolution. Yeah. There's been. Actually, recently there's been a kind of a surge of calculi and analyses for QBF. Okay, so we have this theoretical and empirical analysis. Of course, now I think that the hard question now is who cares outside of the QBF community? Right. So I'm happy to say that many excellent people have picked up some of these ideas and implemented in other settings. So, namely, there's been some work in circuit synthesis. There's a paper from SRI which actually takes this approach and lifts it or generalize it for a fragment of first-order logic, which I think is amazing. Then there are some papers for games, so verification of these. So there's this correspondence between games. So this is what we expect. Recently, I learned about this paper that is using directly my solver to solve some verification problems in multiple clock domain. I still haven't quite understood this domain, so this is something I'm learning about. So I think this is really nice. So we have seen some fruits of these ideas that really people are picking them up and using in other settings.
To clarify, you're saying that your algorithms have been picked up by these 6 different teams to do their thing.
Yeah.
Okay, great.
Yeah, but what happens that I think my disappointment here, and this is what I would like to get on to now, is they're not really using the solver. Right? They're kind of using the idea, but not the solver. And this is one question for us, right, who write the solvers. How do we improve the solvers so people can really use them kind of out of the box, right?
So they're taking the ideas and the algorithms and, I don't know, somehow doing their own implementation? Or but not taking your code? Is that what you mean?
Yeah. So I mean, the idea would be that they take their problem, encode it into QBF, and run my solver. Right? But apparently, too much information is probably lost in the translation to QBF. So I think so. I was thinking about this. What is my vision for QBF? How do we go on from now? So I think this is maybe rather trivial, but I think we're lacking in this in the QBF community now. There's these 3 pillars: the solvers and the ideas behind them, the people that use the solvers, or we would like them to use the solvers, and the theory, right? And we would really like to have tight interaction between 3 pillars. So we build a solver, we give it to the users, they're not happy with it, we build a better solver, and similarly, we build a solver, we analyze it theoretically, and improve the solvers. So I think this is what I've been trying to do, but it's of course hard. So I'm actually happy to always to show people like here that I know that you're using quantification in your work. So hopefully we can. I could also learn from your applications, and maybe we can generate benchmarks and so on.
So SAT solvers have very standardized API these days.
Yeah.
Little input languages.
Yeah.
So it's very easy to plug a new one in.
Yeah.
Is the same true for QBF?
There is, but actually it's more of a downside than. So actually, what has happened is that people just build on SAT solvers, right? So SAT solvers use CNF. So QBFs were built on CNF. And now what has turned out is that it's very bad. So actually going to CNF from, let's say, a circuit is detrimental to QBF. Okay. So actually...
I see. So the standardized input language is a bad one.
Yes.
So you've got to change the standardized input language.
Yes. So I mean, there's been some recent work to come up with a language that would be non-PreNext and non-CNF. So of course, and now that's the issue. It's no longer easy, right? No, I mean, it's easy, but it's. I mean, compared to DIMAX to CNF, it's all of a sudden we are talking about some circuit graphs and some. So the implementation of parsing, let's say, is all of a sudden much harder. Right?
But until you have that standardized interface, this interplay between users and solvers is just not going to happen.
Yes.
So that's a high priority for you.
Yeah. I mean, there is one version already out. So okay, to concretize some of these ideas. So one thing that we already came up. So we have new calculi for QBF, but no solvers that correspond to these calculi. So we should look into that. We should understand better why is it that the solvers fail to apply in these scenarios. So people use the idea, but not the solver, right? So that is really, that should be somehow something that we should be able to overcome. And what this might also entail is to generalize. What seems to be really a high priority now is quantified bit vectors. So actually, one of the papers that I shown is using yikes instead of a SAT solver. Right. So I mean, you take my algorithm and you replace it with yikes, and so then the solver already knows how to deal with bit vectors. Okay, this kind of concludes this presentation about what I've been doing on QBF in past few years. So I hope I convinced you that we have some nice algorithm for solving QBF, and that is both interesting both empirically and theoretically. I would also put some advertisement here. So I've been, if anybody is interested, I've worked on other tools in the past few years. So like package management systems. I've also built a MaxSat solver, and there's some other smaller tools that you can see on my website. Okay, so this concludes my talk, and I'm happy to take questions. Thank you.
I have a question. So it looks like if you consider the algorithm actually this CEGAR loop, it's not that tightly connected to the Boolean case, and so that's what you also hinted, that you can plug in yikes instead of SAT solver. Have you considered going sort of to other sort of theories beyond Boolean? So you have the Q and F, but flip, take out the B and sort of replace integers, what Simon loves so much.
Yeah, I mean, I was thinking about this a little bit. I talked to Nikolai Bjerner this summer about this, and so I mean, it's too early for me to say some definite answer. Of course, it's not easy because we're considering, we know that in this case the set of moves and counter moves is finite. So we know that it will terminate. So we need some way, for integers, let's say, we need some way of actually grouping the counter moves and moves into some sets that make the whole set finite, right? And we kind of hope that, well, maybe it should be possible. So I mean, of course, you know very well there's these decision procedures for linear arithmetics, or where you actually are able to split the space into some finite set of polyhedra, or so maybe this could be applied in these settings, but it's still I'm not sure at this point, but it's something that I've been also considering. Yes. So.
Okay, thank you. More questions?
So in the counterexample-guided thing that you described, there was two calls to solve, right?
Yeah.
And the first one of them was to do with sort of avoiding choices to kind of guide you. It was a kind of, you could think of it as a heuristic, right? You say, try to avoid choosing a mu with choosing a tau prime that has a losing move. So you don't have to have guaranteed answers there. Could you imagine having some approximation to solve? Some much quicker decision procedure that would say, well, it looks as if it's likely that it would have to consistently err on one side or the other. Do you see what I mean? You don't have to have completely precise answers for the guiding part, do you?
Yeah. Well, I mean, you want to guarantee completeness, right? So you need some guarantees. I mean, I think let me give two answers. So one is that you can actually try to look. You actually go the other way, that you want to have a heuristic for searching for the candidate, right? So you want to find not only a winning move for the approximation, but a good winning move for the approximation. So this is like making it actually harder than easier. Then what I saw actually recently, so Nina Naroditska, what she did in her work for solving these games, what she did was that instead of considering this smaller game, so if my understanding is correct from the paper, is that she would say that we're not solving this this abstraction as a smaller game, but we're assuming that the opponent is collaborating with us. Actually, we're assuming we have a stupid opponent, right? So this maybe answers partially. Of course, I mean, I could imagine there could be some more heuristic approach, maybe based on local search or yeah. I mean, but of course, the problem is how to ensure completeness if you insist on that, right? I mean, maybe you don't, but I always try to build things that are complete.
Some people ascribe only limited intelligence to the opponent. They assume that the opponent is operating a strategy, and that strategy is somehow bounded by notations or complexity. We, the good guys, only have to protect ourselves against that degree of intelligence. And making strategies explicit, which you do in your theoretical construction, might be a way of guiding the search for a solution.
Yeah, this is an excellent point. So actually, it took me some time to realize exactly this, and I have some ideas for this. So actually, what is happening here? There is an implicit strategy, as you're saying. So actually, the strategy is we're building a strategy that is getting stronger, right? We're thinking the opponent. Initially, we try an opponent that always plays the same move, right? And then we build a strategy where he tries these two moves, right? And then we try a strategy that tries, and so on and so on. But of course, it actually, and this was also you asked that at the beginning, this might altogether be really bad because these are constants. It might be much better to consider a function that looks at what the opponent played and calculate the answers. I mean, now we have, essentially it's an if-then-else strategy, right? So essentially we're considering a strategy that is just, oh, let me try that, let me try that, let me try that. Yeah.
Table lookup.
Yeah, table lookup. So of course, the hard part is, how do you, the problem is that you need some good search in this space of strategy. So that's hard. Because, I mean, so in constants, it's a nice search because we just go one vector at a time. But for strategies as a set of functions, all of a sudden it gets more complex.
I would say we take the last question. Andy, you raised your hand before.
I can take it offline.
Okay, let's thank Mikolas again.